Picture a city of 2 million people on a Tuesday morning. Nothing dramatic has happened yet. There is no explosion, no warning siren, no declaration of emergency. But inside the control room of the regional power grid, 3 operators are watching a cascade of alarms they have never seen simultaneously. Transmission lines are tripping offline one by one. The load is redistributing across fewer and fewer pathways. Each redistribution adds heat and stress to the remaining lines. The operators know what is coming. They have read the incident reports from the Northeast blackout of 2003. They understand what happens when you cannot shed load fast enough, and within 8 minutes, they lose the ability to stop it. What those 2 million residents will not understand, not that morning, not that week, is that the power grid was not the first system to begin failing. It was the fourth. 3 other critical utility networks had already begun degrading quietly, invisibly, in ways that made the grid collapse not just possible, but mathematically inevitable. This is what infrastructure collapse actually looks like from the inside, not a single dramatic event, but a specific sequence, a precise order in which systems fail, each failure making the next one faster and harder to stop. Understanding that sequence is not optional for serious preparedness. It is the entire foundation of it. The first system that degrades before a visible collapse is almost always telecommunications infrastructure, and almost nobody prepares for this correctly. Most people treat communication as a convenience layer on top of survival systems. This is a catastrophic misunderstanding of how modern infrastructure actually works. Telecommunications is not a passenger riding on top of the grid. It is the nervous system that coordinates every other utility network in real time. The power grid uses it to balance load across substations. The water system uses it to manage pump stations, pressure zones, and treatment chemical dosing. The natural gas network uses it to monitor pipeline pressure and operate remote shutoff valves. When telecommunications degrades, all of those systems lose their coordination layer simultaneously. They do not immediately fail, but they begin operating blind, and blind systems make mistakes. The hidden science here involves something called SCADA, Supervisory Control and Data Acquisition. These are industrial control systems that sit behind almost every major utility network in America. They depend on continuous data links to function. When those links degrade, operators lose real-time visibility. They switch to manual protocols, which are slower, less precise, and far more prone to human error under stress. The 2003 Northeast blackout, which cut power to 55 million people across 8 states and parts of Canada, was significantly worsened by the failure of a single utilities alarm system in Ohio. That alarm system failure was a telecommunications and software issue, not a physical grid issue. The grid problems were real, but operators could have managed them. What they could not manage was working blind. The lesson from that event was direct. Degraded communications do not just slow your response, they distort your entire picture of the system state. You are making decisions based on data that is minutes or hours old, which in a cascading failure is the same as making decisions based on nothing at all. For preparedness, this means your earliest warning signs of a serious collapse are not power outages or water pressure drops. They are subtle communication failures, cell towers going to battery backup, data speeds dropping, landline quality degrading, emergency broadcast tests becoming irregular. These are not coincidences. They are the first symptoms of a system losing its coordination capacity. If you wait for the lights to go out to begin your preparation, you have already missed the first system failure by hours or days. Your response window has compressed significantly, and you do not even know it yet. The second system that weakens before collapse is fuel supply infrastructure, specifically the distribution network that moves refined petroleum products from terminals to end users. This is not about oil wells or refineries. It is about the quiet, unglamorous network of pipelines, truck depots, and storage terminals that gets fuel to gas stations, hospitals, backup generators, and emergency vehicles. Most Americans have no mental model of how fragile this distribution network actually is under stress. The average gas station in the United States holds between 20,000 and 30,000 gallons of fuel in its underground tanks. Under normal conditions, that station sees deliveries every 2 to 4 days. Under a regional emergency, demand surges while delivery capacity contracts simultaneously. The math on that equation is not forgiving. What most people miss is the dependency loop buried inside fuel distribution. The trucks that deliver fuel to gas stations run on fuel. The terminals that store and blend fuel depend on electricity. The pumps at those terminals depend on electricity and, in many cases, natural gas. When grid stress begins and telecommunications degrade, fuel terminals start losing automated management functions. Operators have to make decisions about allocation manually. They prioritize differently than automated systems do. Critical facilities, hospitals, emergency services, government operations get allocation priority under formal emergency protocols. But the civilian distribution network, the one that keeps ordinary gas stations supplied, gets deprioritized. This is not a conspiracy. It is standard emergency management doctrine. It is what is supposed to happen. The problem is that the civilians who depend on that distribution network have no way of knowing it is happening until they pull up to a pump and find it empty. The historical record on this is consistent. During Hurricane Katrina in 2005, fuel distribution collapsed within 72 hours across a wide area, including zones that had not been physically damaged by the storm. The distribution infrastructure was intact, but without telecommunications coordination, without functioning payment processing systems, and without drivers willing to enter the affected zone, the network simply stopped moving product. During the Colonial Pipeline shutdown in May 2021, a ransomware attack that affected only billing systems, not the physical pipeline itself, caused fuel shortages across the Southeast within days, not weeks. Panic purchasing amplified the effect, but the underlying cause was a loss of coordination capacity in the distribution network. When a distribution network loses confidence, it stops. Product does not move. And when product stops moving for more than 48 hours, the downstream effects on every other critical system begin compounding. Your survival implication here is concrete. Fuel storage is not hoarding. It is load balancing against a distribution system you know will fail under stress. Properly stored fuel, rotated and treated with a stabilizer like PRIG or STABL, remains usable for 12 to 24 months. A family that maintains 40 to 60 gallons of treated gasoline and 20 gallons of diesel is not preparing for the end of the world. They are buffering against a documented, historically recurring distribution failure that happens in virtually every regional emergency of significant scale. Vehicles become your mobility asset. Generators become your power buffer, but only if you have fuel when the stations go empty on day 2. The third system to weaken is natural gas distribution. And the failure mode here is distinct from anything most preparedness guides address properly. Natural gas in America travels through a layered network. Interstate pipelines carry high-pressure gas across the country. Local distribution companies, or LDCs, step that pressure down and move it through medium-pressure mains. Service lines reduce it further for home delivery. The entire system is pressure-driven. Gas does not need pumps to move through the final distribution network the way water does. It moves because the upstream pressure pushes it forward. This seems like a resilience advantage, and in normal disruptions it is. But in a serious multi-system collapse, that same pressure-driven architecture becomes a vulnerability. Here is the hidden engineering detail that almost no preparedness discussion touches. Natural gas distribution systems require active management at every level to maintain safe operating pressure. If upstream supply drops while downstream demand remains constant, system pressure falls. At a certain pressure threshold, different for each system but typically in the range of half a pound per square inch at the service level, appliances stop working reliably. Pilot lights go out, flame sensors trip, but the gas does not necessarily stop flowing immediately. Depending on system design, low-pressure gas can continue moving through lines for hours after appliances have gone offline. When pressure eventually drops below the operational threshold and the system depressurizes significantly, the local distribution company has to physically purge and re-inspect every service address in the affected area before they can go back online. This process, called a system restoration after an uncontrolled depressurization, can take days to weeks. It requires technicians to physically visit every service address in the affected area to inspect and relight appliances before the system can go back online. After the gas explosions in Lawrence, Andover, and North Andover, Massachusetts in September 2018, caused by a pressure over event rather than a pressure drop, but requiring the same restoration process, it took Columbia Gas of Massachusetts roughly 3 months to restore full service to the 8,500 affected customers, even with extensive outside resources mobilized. The physical labor of restoring a gas distribution network after an uncontrolled event is staggering. It scales with the number of service addresses, not with the severity of the initiating event. In a regional collapse scenario where technician availability is also degraded, restoration timelines could extend dramatically. Households that depend on natural gas for heat in winter are not facing a one-week inconvenience. They are facing a multi-month heating failure at the worst possible time. The survival implication is direct and urgent. Any preparedness plan that includes natural gas as a primary or backup heating source needs a non-gas contingency that can operate for 60 to 90 days at minimum. Propane heating systems with properly sized tank storage, kerosene heaters with appropriate ventilation protocols, high-efficiency wood stoves with approved fuel storage. These are not backup plans. In a serious collapse scenario, they are your primary heating system, and you need to be ready to use them the moment gas pressure begins behaving erratically, not after the system is fully failed. The fourth system to fail is the electrical grid, and this is where most people anchor their entire collapse model. This is correct in one sense. Grid failure is the most visible, most dramatic, and most immediately disruptive of the 6 utility failures. But it is critically wrong in another sense, because by the time the grid is visibly failing, you have already missed 3 prior warning windows. You are not at the beginning of a collapse, you are at its midpoint. The grid has already lost its telecommunications coordination layer, its fuel distribution support, and its natural gas generation capacity. What you are watching is not the cause, it is the consequence of a system that has been degrading for days. The engineering reality of grid failure is more complex than most people understand. The grid does not simply switch off. It undergoes a cascade of protective actions designed to prevent physical damage to expensive, irreplaceable equipment. Transformers trip offline. Transmission lines disconnect automatically when current exceeds safe thresholds. Generation units drop when frequency deviates from 60 Hz, the standard operating frequency for the American grid, beyond acceptable tolerances. Each protective action shifts load onto remaining equipment, which pushes that equipment closer to its own trip threshold. In a serious cascade, this process can progress from stable grid to widespread blackout in minutes or even seconds. The Northeast blackout of 2003 went from a recoverable situation to a full cascade in approximately 9 minutes of uncontrolled propagation. What this means practically is that you cannot simply wait and watch for grid degradation over time and use that window to respond. The actual grid failure event is nearly instantaneous from the perspective of a household. Your response window is not during the cascade. It is in the hours and days before the cascade, when the upstream system failures are still partially observable. This is why the sequence matters so profoundly. Every system that fails before the grid gives you an information signal and a preparation window. Degrading telecommunications means you have days, not hours. Fuel distribution failures give you 24 to 72 hours. Natural gas pressure irregularities give you hours to days. If you have paid attention to all 3, your grid response, activating backup power, filling water storage, securing food and medication, is already complete by the time the lights go out. If you have not been watching, you're scrambling in the dark with a million other people and the stores are already empty. The fifth system to fail is municipal water, and this failure is where life safety risk escalates most severely. Water treatment plants are among the most underappreciated professionals in American infrastructure. Municipal water systems are extraordinarily complex engineering achievements that operate at enormous scale under strict public health requirements. But they share a critical dependency with every other system on this list: electricity. Water treatment plants require continuous electrical power to run filtration systems, chlorination dosing equipment, UV disinfection arrays, and pumping infrastructure. Water distribution systems require electricity to maintain the pressure that moves water from treatment plants through mains to homes. Most large water systems have backup generation capacity for critical facilities, but that backup generation capacity is limited in duration and dependent on, here it is again, fuel supply. The hidden failure mode in water systems is not the dramatic one people imagine. Taps do not simply stop working suddenly for most of the affected area. What happens first is pressure degradation. Municipal water systems operate at a target pressure of between 40 and 80 pounds per square inch at the service connection. As pump stations lose power or fuel, pressure begins dropping. At reduced pressure, water still flows from taps, but more slowly. Upper floors of multi-story buildings lose pressure first. Fire suppression systems go offline when pressure drops below their operating threshold. The water that is still flowing may not have been treated properly if chemical dosing systems have been disrupted. Boil advisories go out. Then, as pressure drops further, the risk of backflow contamination increases. When a water main is at positive pressure, any crack or joint failure pushes water outward, keeping contaminants out. When pressure approaches zero, that protection disappears. Contamination can enter the distribution system through any compromised point, and at that stage, the water coming from your tap is not safe even if it is still flowing. The documented timeline for this progression in serious emergencies is typically 3 to 5 days from grid failure to significant pressure degradation, and 5 to 10 days to complete system failure absent emergency restoration. This timeline is not universal. System size, backup generation capacity, fuel availability, and operator staffing all affect it, but it is a useful planning baseline. What it tells you is that water storage is not about surviving a 2-day inconvenience. It is about bridging a gap that could extend for weeks. The standard emergency management recommendation of 1 gallon per person per day for drinking and cooking, the minimum, requires 14 gallons per person for a 2-week bridge. Adding sanitation requirements, a realistic figure is closer to 3 to 4 gallons per person per day, meaning a 2-person household needs 80 to 100 gallons of stored water to maintain basic safety for 2 weeks. Most American households have essentially zero. Water purification capacity is equally important as storage. Mechanical filtration, specifically filters capable of removing biological contaminants, a Sawyer squeeze, a Berkey gravity filter, a Life straw, combined with chemical treatment capability using unscented household bleach, calcium hypochlorite pull shock, or iodine tablets, gives you redundant purification options against the contamination scenarios that emerge when distribution system integrity fails. This is not theoretical preparation, it is the documented requirement that emergency management agencies in every major American city include in their official preparedness guidance, which the overwhelming majority of residents do not follow. The sixth system to fail, and in many ways the most consequential for long-term survival, is sanitation and waste management infrastructure. This system almost never appears in preparedness discussions at the level of analytical seriousness it deserves. People prepare for no lights, no gas, no water. Almost nobody prepares for what happens when the sewage system fails, and the consequences of that failure are historically the most lethal of all infrastructure collapse outcomes.
Modern sanitation systems are not passive gravity drains. Urban sewer systems include pump stations, called lift stations, that move wastewater uphill or across flat terrain to treatment facilities. Those pump stations run on electricity. When grid power fails, lift stations switch to backup power if they have it. Many do not. When lift stations lose power, sewage backs up in the collection system. If the failure is brief, the backup is manageable. If the failure extends, sewage begins appearing at the lowest points of the collection system: floor drains, ground floor toilets, basement fixtures. This is not an inconvenience, it is a serious public health emergency. Raw sewage contains a wide spectrum of pathogens, including cholera, typhoid, hepatitis A, E. coli, and norovirus. Historically, waterborne disease transmission following infrastructure failure has killed more people than the initiating disaster event itself. The 1900 Galveston hurricane killed between 6,000 and 12,000 people directly, but the epidemics that followed infrastructure collapse after major disaster events in the pre-antibiotic era routinely doubled or tripled the direct death toll. Modern medicine provides protection that the 19th century did not, but only if medical infrastructure itself remains functional. And in a serious collapse, it may not. The failure of sanitation infrastructure creates a disease vector that can propagate through a population faster than any emergency medical system can manage, particularly when that medical system is simultaneously stressed by every other consequence of the collapse.
Your practical preparation for sanitation failure involves two capabilities. The first is the ability to contain and manage human waste safely without functioning sewage infrastructure. Composting toilets, chemical camp toilets, or a properly constructed emergency waste disposal system using sealed containers, lime, and plastic sheeting give you the capacity to prevent your immediate environment from becoming a disease source. The second is a firm understanding of hygiene maintenance under degraded water conditions. Hand washing with soap and a small amount of water before food preparation and after waste handling provides enormous disease prevention value relative to the water volume it consumes. These are not comfortable topics. They are the topics that separate people who survive extended infrastructure failures from those who become casualties in the second wave. The sequence, then, is this. Telecommunications degrades first, stripping coordination capacity from every downstream system. Fuel distribution falters second, eliminating the mobility and energy buffer that emergency response depends on. Natural gas infrastructure begins experiencing pressure instability third, threatening heating and cooking capacity in ways that may not resolve for months. The electrical grid fails fourth, transitioning the situation from degraded to critical across all systems simultaneously. Municipal water pressure begins dropping fifth, creating a life safety countdown that most households are not equipped to manage. Sanitation infrastructure fails sixth, introducing the disease vectors that historically produce the highest long-term mortality in collapse scenarios. Understanding this sequence reframes everything about serious preparedness. You are not preparing for any single event. You are preparing for a specific, documented progression of failures that follow a real engineering and operational logic. The systems that fail first are the coordination in energy systems that everything else depends on. The systems that fail later are the distribution in sanitation systems that those coordination networks were managing. Every step in the sequence makes the next step faster, more severe, and harder to interrupt. The people who survive extended infrastructure failures without serious harm almost universally share one characteristic. They understood the sequence before it began. They did not wait for a single dramatic event to trigger their response. They watched for the early signals, the telecommunications degradation, the fuel distribution strain, and they used those signals as the lead time they were designed to provide. They had water stored before the water system failed. They had fuel secured before the fuel stations emptied. They had heating alternatives operational before the gas pressure dropped. They were not reacting to a collapse. They were observing its progression from a position of relative stability, making measured decisions instead of panicked ones. The hardest truth about infrastructure collapse is not that it is catastrophic. The hardest truth is that it is legible. These systems follow engineering principles. They fail in documented patterns. The information exists in the public record of every major infrastructure emergency this country has experienced in the last 50 years. The Northeast blackout, Hurricane Katrina, Superstorm Sandy, the Texas winter storm of 2021, the Lawrence gas explosions. These are not mysteries, they are case studies in the exact sequence of failure this discussion is outlined. They tell you what happens, in what order, and why. The only question that remains is whether you decide to read them before the sequence begins again or after. The sequence always begins the same way, quietly, with systems you thought were working fine.